Hello, my name is Burak, and this video is about regression. It's also called regression analysis, not to be confused with linear regression. That's just one way to solve a regression problem. Regression itself is a much broader concept. I've seen a few videos about the theory, but not much about an in-depth practical understanding of this problem. Are you interested in predictive modeling, data science, or machine learning? Maybe you have a difficult regression problem you're working on right now. If so, continue watching. Regression is the mother of all predictive modeling or predictive statistics. It's a fundamental concept and it's everywhere. So if you look at some of the most advanced artificial intelligence architectures under a microscope, you'll find there's a lot of regression going on there. Firstly, we'll talk about the theory a little bit, go through a few examples, and define the context of this problem. You may skip this part if you're already familiar with the theory. Secondly, we'll make our own dataset to study the very nature of this problem. That's the best way to learn. Take my word for it, you'll understand why at the end of this video. Lastly, we'll adjust our dataset to make it more complex and more realistic. This will enlighten us about the real-life challenges and give us a window of opportunity to study the root causes of those challenges. Okay, let's start with the theory. Okay, imagine you have a data set of temperature readings in Celsius and Fahrenheit, but you don't have the function to convert one to another. Question, can you estimate this conversion function by analyzing this data set? In other words, if someone was to give you a reading in Celsius, which doesn't exist in your dataset, can you convert that to Fahrenheit? The answer is yes, and this can be solved as a regression problem. Actually, it would be a very simple regression problem. The dataset you're given is your training dataset to train your model. You can think of Celsius as a predictive variable and Fahrenheit as a response variable. You can solve this as a regression problem using one of the many methodologies, and you will come up with a function which takes Celsius reading as an input and gives you Fahrenheit as the output. So in the broadest terms, in a regression problem, you have at least one predictive variable and one response variable. There are also other names for these. Predictive variables are often referred as uppercase X, x1, x2, x3. Response variable as lowercase y. Generally speaking, these variables are continuous numbers. So they're a number with a decimal part. Here's another example. We're trying to predict the height of a person. You have a training data set with three predictive variables: height of the mother, height of the father, age of the person. This is a more complex problem than the first example, isn't it? For starters, you have multiple predictive variables. They all seem to be useful in predicting. However, even if you have a million rows in your dataset, you won't be able to come up with a function which can precisely predict every single time. Because there are so many factors in determining a person's height. And you have only three of them in your dataset. So you'll have a margin of error here. Whereas in the first example, Celsius is a perfect predictor of Fahrenheit. So if you have a large enough data set, you can solve that one with no margin of error. Coming back to this example, let's imagine we found a new column in our data set. Person's biological gender, male or female. This is useful information, isn't it? Knowing whether the person is female or male should help us predict better. So if we train our model with this additional x, we'll have a smaller margin of error. Because we captured one more predictive variable, which is useful in its own right. But hold on a second. Male or female information is not a continuous number. It's a category, isn't it? Can we incorporate that in our modeling? We can. There are a couple of methodologies for incorporating categorical variables into predictive modeling, but we won't delve into that in this video. Take a look at this graph. Let's imagine it's now midday, and maybe you're interested in predicting what's going to be the value at 1 p.m. You can take past values as your predictive variables and solve this as a regression problem to predict the next value. This is a more specific problem, isn't it? It's a time series. Data is chronologically ordered, but it's still a regression problem because you're predicting a number from other numbers. Here is our last example, a very common problem in commercial domain. We're trying to predict the churn risk of the customer. Churn is when customer chooses to stop using our products or services, so they are no longer a customer. It would be a great commercial advantage if we can predict the churn risk accurately because we can do something about it today to reduce that risk, so customer stays. From the company database, looking at the historic data, maybe we can produce a training data set with a number of predictive variables. Discount rate, number of services customer has on their account, their last bill amount, and tenure, which is how many years they have been a customer. So if we take a snapshot of this data as it was 3 months ago, we can tell whether customer has churned or not in the last 3 months, can't we? You can already see this regression problem is different than the previous examples because our response is either customer churned or not. 0 or 1. It's a binary. Our data set will show 0 or 1 as the response variable. But our trained model will give us a probability. That's how it works. The trained model will give us something like 80% risk of churn or 22% risk of churn. Because probabilities are always between 0 and 1, we don't want to see a prediction with 200%, right? That wouldn't make sense. All predictions must be a probability, and to achieve that, we need to add an extra layer to regression model. It's now called logistics regression because of that extra layer, and it takes its name from the name of the function in that extra layer, which is logistics function. So, 2 more things to mention before we start making data. The famous phrase, correlation does not imply causation. Predictive variables can be very useful predicting the response variable, but there isn't necessarily a cause and effect relationship, is there? Right. In the last example, discount rate probably has causation on the churn outcome, don't you think? If you don't get a good discount, you're more likely to leave. However, in the first example, Celsius doesn't cause Fahrenheit. They are just correlated because they measure the same thing. So how do we train a model on a data set? What are the mathematics involved in that process? Remember, the model's objective is to approximate the conversion function. Here's how it works. You define a cost function. You can think of this cost function as the holistic view of your error rate for the current model. Then you look to minimize the value of this cost function. In other words, cost function is the technique for evaluating the performance of your model. In regression problems with a continuous y, like that example, the default cost function is mean squared error, also shortened as MSE. If y is binary, like the previous example, then you need a different cost function. That one is called binary cross entropy. We'll only cover mean squared error in this video. It's very robust. It has stood the test of time. It's been around for a very long time. Unless you have a very good reason not to, always use mean squared error for this type of regression problems. We'll manually calculate mean squared error in the next section, and I think we're now ready to make some data. I'm on Google Sheets. You'll find the link in the description of this video to make a copy for yourself. So if you don't want to, you don't have to code along. We'll start very simple, but by the end of this video, we'll have an advanced dataset which reflects some of the real-life complexities of a modern-day regression application. So we're going to have 8 predictor variables and 1 response variable. Going forward, I'm going to refer predictor variables as x's and response variable as y. I've already copy-pasted the column headers, as you can see. So let's generate some random numbers using a spreadsheet formula called rand. So this formula will produce a random number between 0 and 1. So let's scroll that across and scroll it downward so we have a sample to look at. Here's the thing, every time I change the value of a cell, the randomly generated numbers will update. Let me show you what I mean by that. This is a spreadsheet functionality. It's to do with calculation settings. Unfortunately, we can't turn it off, but we don't need to worry about it. We'll deal with that at the end. So let's start very basic and let's assume the function that produces our y is just a summation of 8 x's. It looks a bit like Celsius to Fahrenheit conversion right now, doesn't it? That's because using x's, I can produce y with 100% accuracy every single time. All I need to do is to figure out that it's doing a summation. So what do we need to do to make this more realistic? To start with, we can add some noise. So here's what I've done. I've defined a noise parameter and set the value at 10%. On column J, I created a distribution which will create values between minus 10% and plus 10%. On column K, I multiplied column J with original y value to find the noise value itself, and column L is the summation of the noise value and original y. So if I change 10% to 50%, you'll see y final values will deviate further away from the original y. Let me show you a little bit more about the column J calculation. So I use the same rand formula there, but remember rand formula will give a number between 0 and 1. So if you subtract half and multiply it by 2, then you get a distribution between minus 1 and 1. Then multiply that with your parameter, then you get the distribution as you need. Here's the thing, column J will not have a bias. It's centered at 0. So if there are enough values in column J, the average would be 0. And that's important. We don't want to introduce bias with noise. I will change the noise parameter back to 10%. And let's take a moment to reflect at this point. We can no longer predict y with 100% accuracy. That's because we've added an element, and this element cannot be explained by the predictor variables. It's noise, and there's no way of predicting the contribution of noise in the y. I'd like to move on to something else now. Let's draw a histogram chart of one of the predictor variables. I picked x5 and I scrolled it down so that we have enough sample size for a histogram. Let's take a look at the histogram. As you can see, values of x5 range between 0 and 1, evenly distributed, every number well represented no gaps. So this is a textbook distribution. It's called uniform distribution. It's very beautiful, but you don't often find this in real life. So to make our dataset more realistic, let's change the distribution function of x5. This formula will produce a number based on standard normal distribution. You're probably familiar with normal distribution, also called bell curve, also called Gaussian distribution, and as you can see, the bell shape. You're way more likely to find this in real life, in my experience. So let's come back to our data set and let's update x6, x7, and x8 accordingly so that they all come from normal distribution. Right. So in our data set right now, half of the predictive variables come from uniform distribution, the other half come from normal distribution. We will revisit this near the end of the video, but for now I'm going to leave it as it is. So what's the next step for making our dataset more realistic? So right now our conversion function is just a summation of the x's. So let's make that more complex. I wrote a function earlier, so I'm just going to copy paste that into this cell and explain it to you step by step. I'm going to also unhide my comments here. Right. So here's how it works. For x1, we are multiplying it by 1.85 and adding it. So between x1 and y, there's a linear relationship. For x2, taking the square root of x2 and subtracting it. For x3, squaring x3 and adding it. So that's a quadratic relationship. For x4, we're taking the natural logarithm of x4 value and subtracting that. For x5, x6, and x7, you may have spotted the if condition in the formula. Let me explain this. Sometimes a predictive variable will only be activated once it reaches a certain threshold. In other words, below that threshold, it has no impact on y, or it has a more limited impact. So that's what I try to represent here. So if you look at x5, it has a threshold of 0.8. When it reaches 0.8, it's multiplied by 0.2, less than 0.8, it has no contribution on y, it's 0. x6 is similar. Here, the threshold changes it from a 0.2 coefficient to 0.1, so halves the effect of it. But when it comes to x7, there's something else going on here. You may have spotted the formula of x7 actually makes a reference to x6. So this is what you may call an interaction pattern. So how x7 is going to contribute into y is determined by the value of x6. So if x6 is more than 0.9, x7 is multiplied by 0.2, otherwise it's multiplied by minus 0.3. So it changes direction based on the value of x. This is again something you'll find in real life. There are interaction patterns between your predictive variables, and this is one way to represent that. So the eagle-eyed among you may have already spotted that x8 is not highlighted when I select the formula. So x8 makes no contribution to y. It doesn't exist in the conversion function. Why is it in our data set? So what happens in real life is you don't know in advance which predictive variables are actually useful in predicting. You find a particular data point from your data set, particular column, and you assume it has an impact on y. but you don't really know, and many of them turn out to be completely irrelevant. So our x8 is the irrelevant variable here. We can hope once we train our predictive model, it will figure out x8 has no impact and it will completely ignore it. In real life, we don't know this conversion function. We can only see the x's and the y. Right now we have two y's. Let's simplify that. Rename the original y to y deterministic and y final to just y. Deterministic in this context means is the predictable element of y. It's the element free of noise. Moving on, let's remember what is the objective of a trained model. It is to find a mathematical approximation for the conversion function, isn't it? What enables that is something we mentioned earlier. It's the cost function. So while training the model, you look to minimize the value of the cost function. In a regression model like this one, the cost function is mean squared error, or MSE. We are going to calculate MSE in our dataset in the next couple of minutes. Here, on column Q, I've improvised an approximation for the conversion function. Created a formula which looks similar, but it misses out some elements, as you can see. Let's assume we already trained a predictive regression model and it came up with something like this. So the trained model figured out what to do with x1, x2, x3, and x4, but couldn't make any sense of x5, x6, x7, and x8. Maybe they were too complex. So column Q shows our prediction for this model, and on column R I have the squared error. Squared error is the difference between the actual value and the predicted value squared. Because it's squared, it's always a positive number. So if you were to take the average of column R, then you reach the MSE for this model. Mean is just another name for average. So what we've done here is the average of the squared errors. Hence the name mean squared error. So on this cell, I have calculated the square root of MSE. And you may be wondering why I've done that. So square root of MSE is also called RMSE, is useful because you can compare it to the average of y. I've already calculated average y, so I'll just unhide that for you. And at this point, let's ask the question, what's the observation here? So average y is around 1.7, whereas RMSE is around 0.38. So RMSE is around 20% of average y. 20% is not too bad. We can tell RMSE is significantly smaller than average y. That's a good thing. So the model has some good prediction power. But remember, making this comparison between RMSE and average y, or sometimes median y, is a very basic way to assess the performance of a trained model. So let's experiment with a better model than this one. Maybe the best possible approximation where the trained model perfectly approximates the conversion function. I have copy-pasted the conversion function on column N because that's the best a trained model can do, isn't it? It's the replication of the conversion function in full, so it's our benchmark. So column N, the prediction of best possible model, will be equal to the values of column I. If that's not clear to you at this point, pause the video and take a moment to reflect. We've got MSE and RMSE calculated for the best possible model, and it shouldn't come as a surprise that it's better than the MSE values of the other model. We can now test some scenarios and figure out the nature of a regression problem hands-on. So let's begin with changing the noise to 90%. Now, both models have a very high RMSE. So compared to average Y, I would say that's a very high value. Neither of them are very accurate at this point. Now let's change the noise parameter to 0 and see how that looks like. Here, the best possible model can predict with 100% accuracy, no error. So MSE value is 0, whereas the other model still has a positive MSE value. So what's the conclusion here? Error in our predictions originate from two things. First one is noise. And remember, noise is the element of Y which cannot be explained by any of the X's. Second one is how accurately the trained model has managed to approximate the conversion function. So in the best possible model, with perfect replication of conversion function, we only see the effect of noise. If noise is 0, then MSE here is going to be 0. Whereas here, it's a mix of noise and imperfect approximation, leading to a larger MSE. So looking at MSE or RMSE is useful, but not enough for a thorough analysis. Maybe it's good at predicting the moderate values, but it struggles at extreme values at the edges. To assess the success of a regression model, we need to visualize the results. Maybe use a sorted scatter plot. The next video will show you how to do that. Let's have a wider discussion to make this dataset and our approach as realistic as possible. When you look at this data, do you think it's clean data? Or do we need to do some work to clean it? The answer is, it's very clean. It's as good as it gets. Normally, it takes a lot of work to improve the quality of data to this level. Let me explain that. Are there any blanks? No. Every cell in every row has a number against it. Are there any inconsistent values? For example, x1 ranges from 0 to 1. Do you suddenly spot a million somewhere in that column? Maybe worse, maybe there's a text instead of a number somewhere. Another check is to look for duplicates. Luckily, we're not going to have any of that in this data set because of the way we create the data. In practice, you've probably got your dataset from a company database. Maybe it includes user-entered data. If so, there will be inconsistencies, and you have to apply data science techniques to clean the data before you start your regression training. Let's talk about scaling. Scaling is a useful pre-training technique. It can improve the effectiveness of the training process. Do you think we need to apply a scaling method here? I don't think so. So some x's range between 0 and 1, uniform distribution. Others have a standard normal distribution. This is how data ranges should look like after you apply scaling. For example, maybe one of your x's range from 0 to 1 million. In that case, you can apply min-max scaling to condense that to a range between 0 and 1. Condensing the ranges of x's is a generally useful thing to do, and remember, you're not losing any information while doing that. You can always convert back to the original. So our dataset is clean and it doesn't need any scaling. Let's talk about quantity. Do we have enough data? Enough number of rows, also known as sample size. Because our data is generated by a set of spreadsheet formulas, we can create as many as we like. In real life, you may not have tens of thousands of data, and that can be a real problem. If you're solving a complex problem, you'll need advanced models, and advanced models require a lot of data. If you're solving a simple problem like converting Celsius to Fahrenheit, then a small data set will be enough. To make this experiment as realistic as possible, we'll have a limit on the sample size. We'll have a 5,000 strong sample, and then we'll have a 50,000 strong sample for the training set. And we'll test both scenarios in the next video. We'll train models and assess the performance of different regression model architectures. Moving on, another subject to discuss is the effect of time. Remember, we have a conversion function which takes x's and produces part of y, produces y deterministic. How does that conversion function evolve over time? In this dataset, it doesn't, does it? Rows are not chronologically ordered, and it's the same conversion function for all rows. Now, that's not always the case in reality. Imagine this was a commercial application and we're predicting the churn rate by using a number of predictive variables. Maybe number of products a customer has, their last bill, discount rate, etc. Customers' churn behavior evolves over time for so many different reasons. So imagine if we had built and deployed a predictive model before the COVID pandemic. It's unlikely to be effective today in the post-pandemic world. That's because the conversion function would have changed. In summary, most prediction models degrade over time, and we need to take that into consideration. I will change the noise parameter back to 10% before I continue. There's one last adjustment I'd like to make on this dataset. Let's draw a histogram of one of the x's and take a look at it. So that's the histogram of x1. As you can see, it's uniformly distributed, there are no gaps, and it looks like it's taken from a textbook. Training a model is easy when you have a textbook distribution of x's, because it can learn from the entire range of data points. You rarely find a textbook distribution in reality, I'm afraid. Often there are gaps, it's skewed, it's asymmetric, and it doesn't look elegant at all. Let's try to speculate why. Imagine this x represents the customer's last bill amount. And let's assume for simplicity, we sell only 3 services. There are only 6 combinations out of 3 services, so only 6 possible different bills. And that data isn't going to look like this on histogram, is it? Realistically, there are probably more than 3 services and many more combinations. But what you'll find when a predictive variable is driven by a finite number of combinations is that its values aren't going to be uniformly or normally distributed. There will be gaps. Some values will repeat many times, other values will never appear, and that's how data generally looks like, particularly in the commercial domain. So let's reflect that in our data set and make the distribution of these x's less elegant, more gappy. Here's a little hack to do that on this spreadsheet. Select a sample of randomly generated data, maybe 30 of them. Copy paste that into a new tab. sort this sample, add maximum and minimum values, and now you can come back to the main tab and make an adjustment on this formula. So instead of generating the number, we will adjust the formula to do just a VLOOKUP into that small sample we've created here. And this adjusted formula will ensure all the numbers on this column come from this sample of 30 odd data points. So let me scroll that down. And now we are ready to take a look at the histogram. As you can see, the same numbers are repeating now again and again, and there are many gaps. It doesn't look elegant, but it looks realistic, so I'm happy with that. Don't worry if you didn't fully grasp the little spreadsheet hack with VLOOKUP. All you need to understand at this point is that we are now picking from this limited sample of data to generate numbers for this column. I've repeated that process to all x's, so all of their values on here come from the narrow samples I recorded on this tab. As you can see, some x's have a wider selection sample than others, and that's intentional. I also scrolled down the formulas to generate a lot of data. So we have 60,000 rows of data now. Remember the spreadsheet calculation, which refreshes randomly generated numbers every time we change a cell? Let me show you that again. As you can see, numbers are refreshing. To stop that, you can simply copy paste the values. So select the formula range, copy, then paste values only. Now let's go back to the whiteboard to recap what we've done so far and set the scene for the next steps. So let's recap what we learned so far. In a regression problem, often there are a number of predictor variables called x's and a response variable called y. There's a conversion function which converts x's into y. A trained regression model tries to mimic or approximate this conversion function. Often, y is made up of two things: y deterministic and noise. Noise is what x's can't predict. You can predict the full extent of y deterministic in the best possible predictive model, but noise will remain as a margin of error in your predictions. We also learned that the association between the x's and y can be very complex. It's not always linear. Sometimes it's quadratic, logarithmic, or conditional, those if statements. And sometimes x's interact. They are not always independent. And often, some x's are not useful at all. We just assume they are, but they don't have any impact on the conversion function. And we don't know that in advance. We also calculated the mean squared error and compared the square root of mean squared error against the average y. This gave us a basic understanding of how accurate the prediction is for the given model. So we know greater noise causes greater MSE. In other words, makes our model less accurate. We also know poor approximation of the conversion function has the same effect, causes greater MSE. So let's say we trained a regression model, but it's not good enough. It doesn't meet our requirements. Its MSE is way too high for our application and we can't implement it as is. What can we do about that? This is what we're going to explore in the next video. We'll look to solve the regression problem of this dataset we just built in the video, and we'll explore the following scenarios: small sample size versus large sample size, biased sample versus unbiased sample, data with a small amount of noise versus larger noise versus quite a lot of noise, and also basic architectures like linear regression versus advanced architectures like random forest or artificial neural networks. We'll be coding in Python on Google Colab, and we'll cover a wide variety of machine learning techniques for solving a regression problem. How do we assess the performance? How do we visualize the results? How do we diagnose the problem? And how do we go about improving the model? Thanks for watching. Hope you learned something new. See you at the next video.